Okay, so a couple things to go over tonight. I'll make a note here. I can't remember who all I sent emails to on the first assignment. I got several that looked really, really good, but it skipped over the reference formatting issue. So I sent out emails reminding people about that assignment. So remember, there's the name requirements. And if everything runs, then all you have to do to meet that requirement is you can just hit Control H and get the Find and Replace dialog box and just change the variable names at the end to match the requirement. But week one was the only really rough one. The rest of the naming requirements are fairly easy to work with. Might as well, while talking about, go ahead and mention this week is juxtaposition, which is just a fancy word to say next to each other. Like that's a term you may have heard it in math class. Like in math class, we often write multiplication with juxtaposition. So like 3 times x, we would just write as 3x. Just means put them next to each other. And as far as variable naming, we do the same thing. We just all the words that spell out a nice description of what the variable is going to be, just put those words together in all lowercase letters. And a lot of Python was written in juxtaposition. So as we move through as you learn more and more about Python, you'll find a whole lot of the methods and objects internal to Python are written in juxtaposition notation, which means all lowercase and the words just put right next to each other with no space or underscore or anything. Just slam the words together. So that's this week's notation, and please pay attention to that. It's worth 10%. So I think everybody that I sent that email to, everything else was great in there. So for the people that got that email, it's the difference between like a perfect score and a low A, knocking 10% off for that requirement. But it's not much of a drop. I just wanted to remind you about it because there are some standards about how we name our variables. So we worked in a juxtaposition this week, which is a whole lot easier to work with to begin with when we get to the examples here shortly. This week we're looking at selection structures tonight and then loops on Wednesday. And then we'll come back and look at another reiterative structure later. That's one thing. It's not exactly my favorite point about the book, how they do loops before methods, which prevents us from doing a faster reiterative structure, which can be really nice in Python because Python's kind of a slow language anyway. It's not the most efficient language, so we lose some speed. So when we can do things that will be faster, it's nice to get back some of that speed, but we have to see methods before we can do the other one. So we'll look at loops Wednesday, but tonight's about selection structures. And before we get into that, just a couple little things to cover. So there's probably quite a bit that comes to mind when somebody says programming or software development, I guess would be a formal way to say it. Programming flows off the tongue a little easier sometimes. But really, programming is about problem solving. Programming is problem solving. So there's a large assortment of people that will take this SDEV 140 class, not just software developers, but the cybersecurity people, network people. We have a wide range of people in this class, and all of us will have problems to solve, and that's why we study programming. Obviously, software developers are going to have much larger problems, but the scripts we write, software developers will write very large programs to solve a particular issue, kind of like this Zoom thing here, right? That's a big piece of software. That's what we think when we say software development. That's why in class and the lectures here, I usually say programming, Because for the cybersecurity people and the network people, you're probably not going to write a program as big as, like, say, Zoom or Microsoft Excel, right? You might do a lot of scripts. Network people, you're going to find you do a lot of things repetitively, same stuff over and over again. So it's kind of nice to automate some of it. So small scripts, but still, you'll encounter a problem. You know, those repetitive actions that you do over and over and over again. And way to solve that is by programming a small script to just automate all those features. Or cybersecurity people's a similar thing. You'll find you're doing a lot of the same checks over and over and over again. So it just makes sense to automate it and have the computer run all those checks because it can do them a whole lot quicker than you can. And then obviously software developers, that's going to be bigger problems. Like the two examples I just used, Zoom here. We need a way to set up video conferencing for people around the world that can work with lots of people at the same time and lots of different meetings. Really large software, kind of a big problem. So it took a fairly large piece of software to solve it. But programming is about problem solving. And in order to solve problems, we need some tools to work with for problem solving. And that's where something comes in called the four constructs. It's been proven that in order to solve any problem, there are four types of tools we'll need. The first one is some sort of sequential tool. So a sequence, an order for things to go in, which what we saw last week in Python, and again this week in Python, it's just going to go in order. For right now, where we're at in Python, it just starts at the top line of the file and just runs each line in from the top to the bottom in the order we write them in. Here in a couple weeks when we introduce methods, it'll be similar, but we have to define a starting point and it might jump around, not necessarily go from top to bottom. We'll split it up in sections and they kind of jump around, but we'll define the sequence uniquely there. But that's the first type of tool we need in order to solve a problem, is the sequence in which the steps for the algorithm have to be carried out. If you all remember the word algorithm, would have shown up a lot in your SDEV 120 class. That means the steps necessary to solve a problem. Or, well, in our case, to solve a problem. The steps necessary to carry out a task would be a more generalized definition of algorithm. Just break it down and every little step that we need in order to do something. The second sort of tool that we need in order to solve a problem is some sort of selection tool. And that's what we're going to be looking at tonight. Ways to make choices. You might remember back in your SDEV 120 class when we were doing everything with the flowcharts. Going through the flowchart, we don't always want to just start at the beginning and carry out the same steps in order. Sometimes we need to make choices along the way and take different branches through our flow and split it up so that different things could happen depending on the given situation. So that's the second construct, so some sort of tool in order to make selections. The third tool we'll need to solve a problem is a reiteration or reiterative tool. So typically the words reiterate and repeat are used interchangeably, right? They mean sort of the same thing. So when I'm giving lectures, I might slip up and say the wrong one sometimes, but I try to separate the meaning for them. So I use repeat for exactly the same thing. And I'll say reiterate for repetition with variance. So the example I like to go with is mowing a lawn. Right? You get out your push mower and you push it down, push it down to mow the first strip. Repetition would be doing that again. Stand behind the mower, push it down, mow that same strip. And then repeating is just mowing that same strip over and over and over again. And I'll split up repeat and reiterate is also use reiterate is repetition with variance. So like mowing the yard, that's like mowing a strip, then turning around and moving over to mow the next strip. That way the yard eventually gets finished mowing. And with that example, sometimes when we're programming, we might want that exact repetition, right? For example, on a website, an animation that's going to run the entire time the user's on the website, right? We want that animation to run in exactly the same way every time. So that would be exact repetition. Normally, we want to use reiteration, as I'm using these words, so that there's some variance and we eventually do something different. We're making changes along the way so that we eventually reach the goal that we're repeating to do. Wednesday night, we're going to talk about reiterative things. Tonight's about selection structures. And the fourth tool that we'll need is some sort of invocation tool. And what that means is that is a way to jump out of our sequence, do some other stuff, and then come back to the exact spot we left our sequence in. So drawing the flow chart, we're going through some stuff. I don't know, a bunch of boxes. I'll just draw dot. But somewhere we might need to have something complicated or something that's going to happen a lot. So we need some way to jump out of this sequence, go do a bunch of other stuff, and then come back to the same spot we left off of in order to jump back into our flow. So that's invocation, the ability to leave and come back. And we'll see some stuff about that next week. But those tools, those are the tools we need in order to solve a problem. Probably didn't need to write that diagram.
Is that kind of like the loop and like the raptor?
Yes,
like a loop?
yes. Loops are the ones we will look at. I'll go ahead and mention it here since you asked. Loops are a tool that's easy for humans to work with. What's natural for a machine is feedback. Not all languages have loops, is the thing. So machines, we can always take our output and send that back to the input. And that's called feedback. You're probably familiar with audio feedback, right? Where a mic, singing to a microphone gets amplified, comes out the speaker and goes right back in that microphone to get amplified again, and then that just creates a vicious cycle. It's a real annoying thing with audio, but some musicians use it as just like another note out of their instrument. That's what machines do naturally. And so every programming language, we can access feedback, and we call that recursion when we're doing that. We'll talk about that after we've seen methods, which I believe will be next week. But it is really hard to work with. So most of our programming languages, they have a structure built in that is much easier to work with, and that's what a loop is. It's a programming language specific way to repeat things. And we'll be looking at those Wednesday night. Does that answer your question, Dustin?
Yep, sure does.
Okay. Yeah, we'll look at all these things kind of in detail and get started on it. What's a good example? I hear cybersecurity people mention Haskell a lot. Is a language that's common for cybersecurity people. And for that one, you have to use recursion, not really good loop structures built into the language. So loops aren't something that's available everywhere, but they are in Python, and that's mostly what we're looking at this semester. Actually, all three languages we'll look at this semester, possibly a fourth one if there seems to be time. Everything we look at this semester will have loops built in, which are much easier to work with. That's the whole point of them. And they're kind of expansion. A loop is kind of an expansion on the selection structure, kind of like the picture. In a flow chart, a selection structure gives us two branches, alternative branches to go. So the idea of a loop, which we're going to talk about Wednesday, is one of those branches we just feed back in so that it just keeps going and going and going. And that makes a nice, easy way for humans to deal with that. But these are the type of tools we need in order to solve a problem. And not just a computer problem. This is problem solving in general. Like the solution to world peace will be put together with these sort of tools. It's just for that particular big one, nobody's figured out the right sequence to the order things need to happen in, or the right choices to make along the way, or what steps might need repeated, or how to leave that sequence and do other stuff and come back to it along the way. Nobody's figured out the right tools to implement that big one, but any problem can be solved with this. If you're hanging out with your friends, watching a TV show or something, and during a commercial break, you stand up and go to the kitchen to get everybody a soda or some sort of drink. These 4 type of tools would solve that problem as well. You know, what order does it need to happen in, right? You go to walk to the kitchen, get glasses out of the cabinet, grab some ice, start pouring different sodas in the glasses. Well, that's the selection structure. You know, maybe one person wants Mountain Dew, another person wants Coca-Cola. So some choices have to be made along the way. And you're pouring more than one drink, so there's some reiterative things going on. You have to fill all the glasses. And invocation, because you might get interrupted, right? Maybe somebody that had told you they wanted a Coke hollers back from the other room that they wanted Mountain Dew instead. So those sort of tools are a problem-solving thing. And since programming is problem-solving, this is what we're going to look at and study as we're learning programming. Do I have anything else in these notes? Nope. Well, these notes have a list of the things I always feel is most important to learn in a programming language, which I will push back to I'll talk about that at the end of the semester after we've seen all those pieces in Python. Or in a couple weeks after we've seen all those pieces in Python, I'll rattle off that list of things that I feel is the most important thing to learn as soon as possible. It's 8 things that tend to show up a lot is that list. But we'll talk about that after we've seen all of them in Python. Any questions about the 4 constructs?
Nope.
Okay, so is it okay if I erase this?
Yeah, that's good. I'm actually on my computer, so I'm gonna join on my PC.
Okay. Yeah, I'm still in the habit of always asking before I erase the board, but I guess with the videos being recorded, if something gets missed from the notes, it's not difficult to pull up the videos and just take a screenshot or something.
I actually pulled up last Wednesday's just to kind of double check on something that I wasn't sure about.
Yeah, that's a good idea. And if at any time you need me to pause to take a screenshot, there's a screenshot feature in Zoom. Y'all know how to do that? Perhaps we should go over that real quick. It was, bring you in on your other computer, and is there a video? I might have to look at the shortcuts again. If you go to one of the places where you can access the settings, like I just clicked the little arrow beside the video camera, and one of the options was the settings, video settings, but it's one settings menu. If you go to keyboard shortcuts, there's a list of all the quick things to do in Zoom. One of them is to take a screenshot. Alt-Shift-T. So if at any point in a lecture, if you need to take a screenshot, just let me know, pause real quick, or you can just be like, oh, say hold on or something. And if you push Alt, Shift, and T, as in train, then yeah, Alt, Shift, T will take a screenshot.
That actually is not. That's not working for me. Let's see here.
Not working?
No. So it's usually what I do for like screenshots, not it copies it to the clipboard. I usually do Windows, Shift, and S.
Yeah, that was going to be what I said. If the Alt Shift T should be the one to take a screenshot and zoom. If it's not working, yeah, Windows key, Shift, and S will give you some little crosshairs to grab a picture real quick. The zoom one is kind of nice because it automatically saves in a folder. So when the meeting ends, you'll have that folder of any screenshots you took during the meeting. But yeah, I hardly ever use that. So I just made a note that it existed. Might be better just to do a regular screenshot, which Windows Shift S on a PC. And if you're on a Mac, push Command Shift 4 or 3. Command Shift 3 takes a picture of the whole screen, and Command Shift 4 will give you little crosshairs where you can take a picture of a section of the screen. Those might be a better way to do that. So next thing I wanted to talk about is, it kind of refers back to something said the first night of class. You might remember I gave this definition for a computer, sort of my definition, what I think of as computer, or really the machines we're referring to whenever we're talking about a programming language. Because some of the things, like this afternoon, I was working on some little microcontroller stuff, which takes a programming language, the same programming language I would use to do stuff on a PC, except it doesn't seem right to call that a computer. So really a machine. But just a general term here, I define that as a machine which can detect, identify, and react to changes of state. So that's really what we're looking at this semester is, with programming, we're telling the computer what its reaction is going to be when a state changes. For example, if I walk over here to the keyboard and push the F key, that's a change, right? Right now, the state of the F key is that it's not being pressed. If I reach over to the keyboard and push that key, then the computer can detect it. And that's all physical hardware. It can, so this part's all physical hardware, and identifies what we're getting ready to talk about. We're going to talk about how it identifies that. And it can react to it. So if I open the chat room and then do that, if I open the chat room, now when I reach over and press one of the keys, like the G key, that's a change of state. I push the key, it's off, push it, now it's on, then release it, it's off again. So the computer detects that change of state, identifies that was the G key that was pressed, and reacts to it by putting that in the chat room. So then when I change the state of the enter key, all those G's that I just typed show up in the chat room. So this semester is really about learning to tell the computer what its reaction is going to be. That's what programming is. And detection, well, obviously that's the physical device itself. You know, like the key, there's a mechanical component that something will change, and then we can register that change. But how do we identify this? And yeah, so often I made a note here to talk about this. We talk about one bit at a time, right? On all these examples, the stuff I write on the board, I often refer to just a single bit at a time, which seems a little small, but remember, this scales directly up. So if it applies to one bit, it applies to hundreds of bits. Or like on my laptop here, it applies to 64 bits at a time. But for the purposes of the lecture, I'm not going to write 64 bits up here. That just wouldn't make any sense if we tried to look at 64 bits on a board in a lecture, right? So we break it down to a smaller example, maybe 4 bits or something. That's quick to write with. But it does scale directly up. So anytime we're talking about binary stuff and talking about, just 1 or 4 or a couple bits at a time, it does just repeat for however many bits we have. And yeah, so that's really what a change of state is. We only have those 2 changes of state, right? 0 goes to a 1 or 1 goes to a 0. That's the only type of state changes we have, which we're talking about an electrical device. So we drew this picture of the first 9 as well. If we plot voltage over time, we'll set up some threshold, and we are either above or below that threshold at any given time. And we're down here below it, something happens, jump it above it, back down for a while, up, and it bounces all over the place because it's electricity. It's going to be bouncing all over the place, but then if we're below that threshold, we define that to be a 0, and above the threshold is a 1. And that's really the only 2 changes of state we could have, is a 0 going to a 1 or a 1 going to a 0. And like I said, detection, well, that's the physical device itself. The mechanical components of the key being pressed, or the button on the mouse, the scroll wheel turning, those sort of things. As far as identifying it, what really happens is the computer just subtracts it. I'll write this. So at every point in time, there's going to be a whole lot of 1s and 0s defining the state of the computer, right? Like my Windows laptop here, 64-bit processing. So everything it does with 64 bits at a time, but it's running several gigahertz. So it's doing that multiple 64-bit processor, multiple 64-bit registers running billions of times a second. There's a lot of 1s and 0s, but at any time the computer can see all of them. And then it can do some simple comparisons. In particular, it can take the difference between 2 states. So let's say at a given point in time, the computer was in this state, 1 0 1 0 1. Do 5 bits for this. And then a split second later, the computer's in this state, 0 0 1 1 0. So to tell if something changed, really the detection, what it does is every pulse through, it finds the difference between those. So we can subtract what, we're just subtracting binary numbers. So 1 minus 0 would give us a 1. 0 minus 1, we have to borrow from this other column, which makes that, well, we borrow 1 from there, which makes that a 2, and leaves 1 over here. Have you all seen borrowing a binary? It looks a little bit different. Why don't I walk through all the steps? We're probably familiar with it in base 10, right? We borrow from the next column over, which is a power of 10 bigger. Which is the same thing, but the next column over is a power of 2. So if we need to borrow, we can view this 1 in the next column as a 2, which in binary is 1 0. Then we'll borrow 1 of those to get a 2 in this column. But we only borrowed 1, so we still have 1 left over here. a lot of people get confused on that and want to borrow this entire one, but remember this one is a power of 2 bigger. If we're going to borrow 2 from it, that still leaves us 1 behind. So then 2 minus 1 leaves us 1. 1 minus 1 is 0. 0 minus 0 is easy, and 1 minus 0 is easy again. So the computer takes the current state and subtracts the previous state. I guess I wrote that backwards. Let's say this is the current state, and subtracts the previous state. And then it can run these bits through an OR gate one at a time to see if they're 0. It'll run those through an OR gate against all zeros to see if there's any ones. And if there's any ones remaining, that means the state has changed, right? Because we had, if the previous state was 1, 0, 1, 0, and the current state is still 1, 0, 1, 0, when we subtract that, we get all zeros. So there's our detection. It can tell it's not all zeros, so that is how it detects a state has changed. And then to identify it, it will look through every reaction it knows to see if any of those correspond to 1, 0, 0, 1, 1, or whatever we get from the difference in those changes of state. Does that make sense? That's how these machines actually operate. We'll look, check the on-off situation of every switch that makes up the CPU and RAM and that makes up the CPU and the registers, and look at all of our on-off switches, find the difference between our current one and previous one, and if it's anything other than all zeros, the computer knows something happened. And then it's going to look through every possible reaction that it already knows about to see if that matches any of these. If that matches a particular change, and then if it does match, it's going to run that set of instructions. So to put that with the previous example, like right now, the G key is not being pressed, so it's in a state of 0. But if I come over and press the G key, I'll turn the chat room back on for the whole thing. I'll turn the chat room on. If I come over here, G is a 0, so if I push G, it's now a 1. Oh, where'd my chat go? It just disappeared on me. It's 0, I push it, it's now a 1, and when I release it, it's a 0 again, so it detected that change. And since it's in the chat room, the enter key is a 0. When I push it, it becomes a 1, so the computer subtracts that 0 from 1, notices there was a change. Oh, there's Jerry. And then it checks to see if that change matches any reaction it knows. In that case, the enter key, which will then take that whatever key I just pressed, the G key, and throw that up in the chat room in this case. So that's how the machines actually detect, identify things. And then the reaction is what we're studying this time. So I don't know if there's anything else I have here. Yeah, so finds the difference between the current state and the previous state, runs that through a series of OR gates to see if it's against all zeros. And if there's any ones remaining, that means something changed. And the computer will take that, the difference between the states, and compare it to every change of state it knows about to see what it's supposed to do. So really what we're doing whenever we program is telling the compute is adding to that list of changes of state, things that could happen. So when the computer comes across any of those, it runs the code. And so you might notice something about the comparison. Depending on how far you're going with software development, this will be important later. It could be important later. You can take advantage of it. Maybe you'll kind of see the patterns and take advantage of it now. People that will continue in the and go on later might notice, normally we talk about Booleans, right? And when we talk about Booleans, we say true and false. And like we're going to look at conditions tonight, and we usually think of those with both the way humans think of them, both our true and our false term, right? But from this thing I just described, that this number right here, when nothing changed, that's what the computer is looking for. So really, the computer is only checking false. And it might, so we don't really have true and false, we have false and not false. And depending on how far you go in programming, that distinction may be important, but it doesn't show up till much later. But it is something that we can use to our advantage and do things quick and speed things up when we need to speed it up. Because it seems like computers have gotten big, but we can still bog them down pretty quick. I think most gamers are well aware of that, right? It doesn't take much to bring the average CPU to a halt still. And it doesn't have to be something as big as a game. I've brought rather large CPUs to a halt just with really big math questions. Like extremely big ones. Are y'all familiar with Wolfram Alpha? Most people have heard of that, right?
Is it a game?
Wolfram Alpha is a math thing. I guess we could call it a calculator, a very high level math thing. So you can just pose math questions and it'll return answers. Here, I'll share my screen and show you real quick if you haven't seen it. But basically, it's an online tool where we can just ask math-based questions and the computer will return the answer. A very, very useful tool. Significant numbers of people have used it to cheat their way through math classes. So that's kind of an issue, but that's on the person. That's not on the tool, right? The tool is useful, and any unethical things are on the person because a computer is not on the computer. But we can just ask complicated questions. So like some sort of math question. Here's a couple of so this looks like just some basic integral stuff. So we can just put in a math question and it will come up with the answer, solve it very, very quickly. With lots of values, different ways to solve it, explanations, all sorts of things like that. Okay. So a very, very powerful computational tool is what it is. But a lot of people that do high level stuff, I've heard the stories from physicists, especially with, if you ask questions hard enough that you lock up their servers, they will block your IP, they will block your MAC address, and you have to actually fill out a form and tell them why you ask a question so hard that it locked up some of the best computational servers, in the world. Because like any server can do a lot of that, but they have a huge server farm dedicated solely to math computation. So if you freeze up their servers, you have to explain to them why you formally fill out a paperwork and explain why you ask such a hard math question. Which I think part of that is just they're curious themselves, just why they put that thing together. But it's very useful. That's if you need a tool to help with math, and stuff, that is a super useful one to look into. But I got a little sidetracked there. does that point make sense? How the computers detect when things change, detect and identify any changes. And then we're doing the reactions. So we're adding to the list of known changes. So whenever it detects a change, it compares it to everyone it knows about. And if anything we programmed matches that change of state, that's when the program runs. I wanted to go ahead and include that, just kind of be thorough in how machines work and what we're doing here. So if there's no questions about that, is it okay if I go ahead and erase this?
Yep, no questions here.
Yeah, because sometimes knowing how the machine works, we can use that to our advantage. Kind of like that small point there. When we're programming in this class, when we write our conditions, what I'm erasing the board to get into right now, well, everybody should have seen it and been introduced to it in the SDEV 120 class. We're going to think about true or false questions. We're going to ask yes or no questions that the computer can answer. But really, that thing I just erased here, the computer only checks for no. So when we ask the question, the computer only checks if the answer is no. And if so really it's not yes and no, it's no and not no. Which, knowing exactly what the machine does, we can use to our advantage if we need to. For most cases, pretty much everything until you're doing really, really complicated things, thinking of yes and no is a much better way to approach it. So that's where we'll get in with selection structures and Boolean algebra and Boolean logic. So machines really are doing math, right? That we talked about that first day, I think. It really, the machines repeat a pattern, and then humans came along and used that repeatable pattern as symbols to do math with. But for the most part, we can say it's okay to go ahead and say the machines are doing math. So that means if we need to make a selection or make a choice along the way, we have to do some sort of mathematical choice, ask a mathematical question. What sort of questions can we ask mathematically?
What's 2 plus 2? I mean,
yeah, and in particular, the part you abbreviated there. What's 2 plus 2? And the important thing, the question isn't the what. The computer's going to do that automatically. The question is this little apostrophe S, right? The is, which mathematically is that symbol, right?
Yep.
Yeah. So, the computer can do this part, and the what is automatic. So the question we can ask is equality, which we already used the equal sign though, right? When we need to create a variable, our variable equals, well, if we wanted to store that, the result of that, we'd do 2 plus 2 is assigned to this variable. So one equal sign, we don't want to use that again. So to ask questions about equality, we'll use 2 equal signs. And that's pretty much across the board. And I always just remember it as 2 equal signs means equal to. Those nice hominin words that sound the same, different words, but it fits nicely with that. 2 equal signs means equal to. What else can we ask about? What else other mathematical questions can we have? Like, we can ask the is question. What's another one? And you don't have to put it in the math class words, because the way we say it in English is often better. Right? In math class, we would say equal to. But like you just said a moment ago, in normal English, we say is. And thinking in normal English when we're putting a program together is probably going to go a long ways towards solving our problem.
Math's not one of my strong areas.
Oh, you've probably seen these before, though. Because we could also ask, like, well, along with what is it?
Oh, is
we could
not.
ask,
Yeah.
yeah, is not. And our symbol for that, we use an exclamation mark and an equal sign.
And of course, like greater than, less than, all that stuff.
Yeah, greater, less, which in normal English we would say more instead of greater than, right? More than, greater than, bigger. I'll write that there. We can ask which one is bigger. That's the question of it. You know, it was like, we can ask the computers, like, here's two numbers, which one of these is bigger or smaller? And that is our greater than, less than symbols, the angle brackets. And we can combine these, right?
Isn't it? Is there is not bigger than, or is that?
Oh, I was looking for the other one. The
equal to or greater than.
Yeah, equal to or greater than, which in normal English we would say at least, which can be very helpful. Greater than, and we have these symbols on the keyboard, but we don't have the normal math class symbol, right? So when programming, we just put those symbols next to each other. We have the greater symbol and we have the equal symbol, so we just put them together like that. And in normal English, we would probably say at least. The words greater than or equal to only show up in math class. Same thing with less than or equal to. In normal English, we'd probably say at most. Which, looking at the normal English terms instead of the math terms can help us, right? If we're adding up a price, well, the first example we're going to do here in a moment, which is probably coming on time for a break. Yeah, so when we do our first example, it's going to be a commission example. And does everybody know how commission works for salespeople? Like,
yep.
Yeah, there's a quota you have to meet just to get your salary. You have to sell so many of the items. But then when you sell beyond that, when you pass your quota, you get a bonus for that. So, you know, if the quota is like you have to sell, I don't know, like a car dealership or something, you have to sell 5 cars a month. I've never worked at a car dealership. I don't know what their quota would be. But anything beyond 5, you get a nice little a commission bonus for the extra sales. We would check at least 5 when we'd say that in English, right? Like if you sell at least 5 cars, you get a bonus. And working in the words we normally talk in can help to put our conditions together. And that's pretty much the questions we can ask, right? Is it something? Is it not something? Is it bigger or smaller than something? Is it at least some number? Like the example I just used, is it at least 5? Which 5 would be okay if we said at least, right? If somebody's going to White Castle, right? We usually eat more than one slider. If somebody's making a run to White Castle, we probably wouldn't just say more than one. We'd ask them to pick us up at least 5, or however many sliders you normally eat. Those little bitty things, one's just not a very big meal. And we can ask at most. So basically the questions we can ask as far as numbers go and the comparisons that the computer can make for us. But that might not quite be enough to do every problem, right? We need to combine some of them. Is it at least 5 and smaller than 12 and smaller than 12? And have two conditions like that, right? And combine different things. Is our number smaller than 1,000 and not equal to 73.5 for some random example? But we might need to combine those. Or age ranges. Oh, like going to the movies, right? Kids and senior citizens get a discount. So if age is under 12 or age is past 65, you get a few dollars off their movie ticket. So different ways that we can combine these things. And that's our logical operators. Really, this is our operators for Boolean algebra. Boolean algebra is a special kind of math that the result is going to be true or false. Where we're not looking for a particular number, we're looking for whether something is true or false, so we can check the conditions, and that's what the computer's returning. And does anybody remember from your SDEV 120 class what our options are for the Boolean operators? How can we combine our conditions?
Can't recall.
Well, I used the words a moment ago, like the movie theater example. Right? Age smaller than 12 or age bigger than 65, there's going to be a discount. Remember that now?
Yes.
So we can combine these conditions with or, which means either one would be okay.
Isn't there and?
Yep. And is inclusive, right? If we say or, either one's okay, right? Smaller than 12 for the movie theater, smaller than 12 or bigger than 65. If we have a kid or an old person, they're getting a discount on their movie ticket. But and wouldn't work at all in that situation, right? Because that needs to be inclusive. Nobody has an age that is smaller than 12 and bigger than 65. That would just rule out every number altogether. So an inclusive one. And we also have not. And another one that's actually a combination that is almost one of the primitive operations is XOR. Did everybody see XOR in your SDEV 120 class?
Yes.
So if anybody didn't watch the video later, that's exclusive OR. So one or the other, but not both. Trying to think of a life in the world example, but or would be if there's any truth to it. So we can think of that as just grasping at straws. If there's any truth whatsoever to the conditions we're asking, we're going to hold on to that truth. Hold on to any little, just grasping at straws. Any piece of truth we can find, we're going to hold tight to it. Whereas and is like a court of law. The truth, the whole truth, and nothing but the truth. It'll only be true on an and condition if everything going into it is true. And not just changes whatever it is. If it's true, a not will change it to false. If it's false, a not will change it to true. An exclusive or is one or the other, but not both. Oh, so for a real world example, like where do you want to go get dinner? right? McDonald's or Burger King. We're not going to both, right? A decision has to be made, one or the other, exclusively one or the other, but not both of them. And that's the ways we have to combine our logic. And then this word, operators. So I wrote logical operators here. That's the way we usually refer to it in computer classes. Before computers, I was in a branch of math called Boolean Algebra. The math questions where the result is true or false, and that's what we make use of in computers. One of the discoveries that led to the invention of computers. So in this type of algebra, well, I'll take a step back. In our regular algebra, we have a bunch of operations, right? You can add things, divide things, work with modulus and work with residues. If you haven't heard that term before, you might hear me say that occasionally. If I say residue, you'll have seen the modulus operator at this point, where we get the result of that is the remainder when we divide. And when the remainder is the part we want, we actually call that the residue, not the remainder. Remainder is like leftover junk that causes problems. But if that's the part we want, the technical term for it should be residue. So you might hear me say that occasionally. That way you'll know what I'm referring to if that just kind of slips out of my mouth. If anybody wasn't familiar, my highest degrees are in mathematics, not, and I just know a lot about computers, how I ended up teaching computers, but my education plan was to be a math teacher. So sometimes the technical math terms will slip out of my mouth. But we have a bunch of different operations we can do with our numbers. Maybe I'll add subtraction, multiplication, and we also have exponents, which Python will let us do two ways. And I think this is one of the textbooks that sometimes uses this for exponents. Have you all seen that in the book for exponents? So technically that's not an exponent. It takes advantage of a certain property in binary numbers so that it works. The caret, the symbol above the 6, that's actually our symbol for XOR. And when we XOR two numbers together, we end up with the exponent in certain ways. So that can be used in Python, but really for Python, our symbol for exponents is going to be two multiplication symbols. Because that, if you remember back in math class, that's what an exponent means. Like 2 to the third power means 2 times 2 times 2. So Python, when they put that together, for notation, they just did repeated multiplication is the symbol for exponents. I'll change this division sign to 1/ because I haven't actually mentioned it in class. It was put in, this stuff was in the book. And that is, if we have 1/, that's our floating point division. The one most of us thinking of anymore, because that's our calculator division, the one that gives the decimal. If we have 2/, then that is our integer division. So like 5 floating point division divided by 2, what is our answer going to be there?
2.5.
Yep. So 2.5. And 5 integer division, the integer division just cuts off the decimal part. It only keeps the integer. So really integer goes with modulus. Then we have the quotient and remainder parts. So we can split them up and work with them that way. So integer division only gives us the quotient, the integer part. So there's no rounding or anything. So like 2.5, we wouldn't round that up to 3. We would just throw away the 0.5 and get back at 2. if you haven't worked with integer division before. But really the easiest way to think about it is, if you remember back in elementary school doing all the division by hand, when we get the quotient and the remainder after dividing, instead of going all the way through the decimal, the integer division goes with the modulus operator to give the quotient and remainder when we divide. But we have those operations, and what got me started into that list is if we were faced with a problem that had a bunch of them, where do we start at? Do we just start at the left and go all the way through like we would reading English? That's a no, right?
Will we start at the end and go backwards?
So there's a particular order we have to do our math operation in. You may have seen it before. I'm going to erase what's in parentheses here, because I need just a little bit more room, and I'm not quite ready to.
It's not PEMDAS, is it?
Yes. Yeah, the order of operations.
All right, I wasn't sure if we did that with this.
We do all the parentheses first. Anytime we're working in math, we have to follow that certain order so we know how to, so that everybody will come up with the same result, right? It's like 2 plus 3 divided by, 2 plus 9 divided by 3. We have to follow our order of operations so that everybody gets the same result. Because if we divide first and then add, we'll get a different result than if we add first and then divide, right?
Yep.
Because one of them would be 2 plus 3, and the other one would be 11 divided by 3. So we have this order of operations that make sure everybody does it all in the same order. Parentheses, exponents. So anything grouped together. We say parentheses, but like a fraction bar has numbers in the numerator and the denominator, so it groups all those together. Or a square root symbol. Everything inside of there is grouped together. So that anything that groups our numbers together counts as parentheses. Then we do any exponents. And we say exponents, but what that really means, if I write an exponent up here, 3 squared, it looks like we have 2 numbers, right? But the way I read that, 3 squared is the operation. So we really only have one number. We only need one number in order to square it. So when we say exponents, that means our unitary operations. The operations only take in one number, which for most people is exponents as far as it goes, but operations only take in one number because that will be important in a second. Then we multiply and divide, and we kind of treat those at the same level. Because multiplication and division are actually the same thing. If you remember way back in elementary school, learned about fractions. In order to divide fractions, we learned to multiply by the reciprocal, and that always applies. Division means multiply by the reciprocal. So those are kind of the same operation, but we treat them as 2 different things. And same thing with add and subtract. We treat them as 2 different things, but we can also view subtraction as add the negative, which makes them the same operation. So we do any groups or operations that only take in one number, the unitary operations, and then our binary operations, the operations that require 2 numbers. Well, for Boolean algebra, we also have an order of operations that it's going to follow. And when our conditions start to get kind of big, we might need to worry about what order they get done in. So obviously we can group these things together. When we write a bunch of conditions, we're programming, we can throw in parentheses and, group things together. So we would do that first. The first step is still the same. We're going to do any groupings first. Anything in parentheses we do first. And then in regular math, the first thing we did was the unitary operations, stuff that only takes in one number. And if we look at these logical operators, or we have to have 2 things, right? 5 or, it's not really an ending point. We need 2 numbers for or. And same thing with and. We can't, and is not a stopping point. We have to have something before and after the and, so it's a binary operation. So those 2 are binary operations. XOR is kind of a special case of or, so it's also a binary operation. But what about not? How many things do we not at once? Just one, right?
Yeah.
Yeah, so we're changing true to false or false to true. We can only change one at a time. So not is a unitary operation. So that's what gets done first. So we do the parentheses first, then our not, and then our binary operations. And to kind of abbreviate this, is anybody going through your math classes somewhere, did you ever hear somebody say, add the ors and multiply the ands? That is something that shows up across the board in mathematics. In a lot of different situations, we add ors and multiply ands, and that's how they fit in the order here. So we do anything in parentheses, the nots, the ands, then the ors and XORs are at the same level. So that's our order of operations for our Boolean algebra, the logical operators, which often doesn't show up because we'll split our conditions up to kind of make it readable, right? We'll do like a condition and then nest another condition inside of it to keep our line small, but there is a specific order to those, and it goes as left to right. So if we have a big, long, complicated condition that has and in it 3 or 4 times, we start at the left and then just work through to the right. Goes left to right as we go through them. But there is a particular order of operations to them. So you want to make sure you're aware of that. And it looks quite different, but it does follow our original order of operations. Any groupings, then the unitary operations, then the binary operations, based on inclusion and scaling. So it's kind of the same thing that, but multiplying, yeah, on a number line, I'll go ahead and draw this. If we add and subtract, we're just moving back and forth on that number line. But when we multiply and divide, that's like we're scaling, like stretching and shrinking the number line. It's like we're changing the size of it. So we do a whole lot of that at once. And the same thing happens with the inclusive operations and the non-inclusive operations. Because and has to have both of them true, and or, as long as either one is true. That's what leads back to the plus and minus, and could drift down a long rabbit hole of talking about why that comes from. But the main point, as long as you can remember, there is a specific order of operations for the logical operators as well, which sometimes will show up if you have more than one when we start putting our conditions together, because usually we want to do more interesting things than just check a single condition, right? We want to do something more interesting than just know if the number we have is bigger than 5. That's a good starting example to learn syntax and stuff, but the problem we're trying to solve, the thing we're putting a script or large piece of software together for, we'll probably have something more interesting than just one single comparison we want to check to make our decisions. So keep the order of operations in mind. So what time is it? 7:13. Okay, so any questions about this?
Nope.
Okay, so why don't we go ahead and take a break, and then we will get in. Now we will get started doing examples of applying all of this in the Python language. So 10 minutes, does that sound good?
Yes.
Sounds good.
Okay. Yes, I am very anxious to go grab some Mountain Dew real quick. But yeah, so it's 7:14, so we'll get started again at 7:24. And I'm going to stop the recording for the break. We don't need to record a break.